Hi, Chloe. How are you? Your scarf looks so cozy. So nice. Hi, what's up?
Not much. What did the class do yesterday?
What did the class do yesterday? What did we do yesterday? We finished off the Pez
Okay.
Kogel. Yeah. We're gonna talk Pez today though. Okay, so yeah. Hello. Hello. Um, I could make one. I will. If it's not ready by tomorrow, can I just post it up on Teams? Perfect. It's my grade nines. Dot and cross, I don't know if you might have ever done them. It's essentially Lewis structures for beginners. I do it with my grade nines, but I don't think anyone else does. It's a British thing to do. It's sort of like, did you do Lewis structures? I don't know if she does. She might. She might not. It's hard to say. Yeah, they're essentially Lewis structures for beginners. Yeah. The only difference is that we continue to draw the circle so that and we draw our dots on the circle rather than just the Lewis structure where we draw the dots without a circle. Still, that way, if it's not a circle, it still kind of looks like atoms.
Remember what this guy said, right? If you skip once, that's okay. If you skip a second, it also happens. But if you skip a third time, things happen. So, Arkansas, so no, here's the deal. Are we really into the two? Any because it's confused, any because
Yay! Today we are going to talk Pez.
then the reason that these two are good.
What's the P stand for? Photo. What does the E stand for? And what does the S stand for? Okay, what do we fire at what do we fire at the atom? A photon, not a proton. They sound alike, it's easy to confuse them. The photon must have sufficient energy to kick an electron, and in fact, not just an electron, but any electron out of the atom. Okay, so what are the chances of it kicking out any given electron? Yeah, there's any given atom, any given electron is the same as any other electron, okay? Yes. Oh no. If you give it a certain amount of energy, it can hop up. But if you give it more energy than that, it can completely escape. Okay. So it is as when an airplane goes up into the air, it has enough energy to get up to whatever it is, 35,000 feet. I don't know what airplanes fly at. But if you have a rocket, it has enough energy to actually escape Earth's gravity. So that would be like this kind of photon. And that's why it has to have sufficient energy. What kind of electromagnetic, what area of the electromagnetic spectrum will our photon be from? Do you know? More than ultraviolet, X-ray. Okay, so if you use ultraviolet, it's not going to be enough to kick them out. It'll just be enough to transition electrons between, like you were saying, between energy levels. But if we provide X-ray, that has a high enough energy. So the probability of any given electron being kicked out is, how would you compare it with any other electron? Is equal. The probability is equal to the probability of any other electron. Yes. So imagine this. You have enough energy to remove any electron. So it just depends which electron the photon actually hits. Yeah? Because the energy is enough to remove any of them, whichever one gets hit will be the one that goes. So the probability of any electron is just as likely as any other. Okay? Now, pardon me? Yeah. Probably not, but you just keep bombarding it with, some will pass through, but if you just keep bombarding it with photons, it'll hit often enough that you'll get a signal. And the signal will be in proportion to how many electrons are at a particular distance from the nucleus. Yeah? Yes? So what we're looking at is we are looking at, let's just use a Bohr model, okay, even though it's not correct, but that's okay. Okay. And we're going to do lithium because it's a simple one. Yes? So we have photons, la 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 la, la 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 la, la la la, la la la, la la la. Okay? Whoa! That one has enough energy to bump that one out. Yes? It also has enough energy to bump that one out. So if I have so out of my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 lines, 12 photons, 2 have hit inner shell. Electrons, and only 1 has hit an outer shell electron, because if you just like throw it at it, that's what you're going to end up with. Yeah? Like if they're all just kind of aimed at the atom. Yes. Yep. Yep. It would, but I'm looking at one atom right now, but in reality, you're not dealing with just one atom. It's going to be a whole sample of lithiums, right? Lithium, 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 lithium. And the light's coming at them. This one, maybe it's an inner electron. This one, maybe it's an outer electron, inner electron, inner electron, outer electron. And that's going to be, like, if you look at it, you know, zoomed in to a single electron, the proportion of inner electrons is going to be twice as high of being hit as the outer electrons, because there's 2 times as many of them. So they sort of just take up more space, as it were, okay? Okay, so while you come up with your question, we're going to carry on. So when we hit the lithium, okay, so now let's, yes. Yes. Uh-huh. Uh-huh. When it falls back down, or? Uh-huh. That's not ionization energy anymore. Okay, ionization energy is specifically the amount of energy required to remove the electron. Okay, so yes. 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 I actually don't know. If I were doing this, I wouldn't bother chucking photons at it that just barely had enough. However, you should be able to describe the fact that if you're throwing energy at these things, the inner electrons they'll be moving with less kinetic energy. And the outer one would be moving with more kinetic energy. I've not left myself enough room to write. So I'm going to the photoelectron, okay? what are we doing? We are shining light on this thing. We are shining all the same wavelength of light. So all of the photons have exactly the same energy. So far, so good? Okay. Okay, and that's kinetic energy. So far, so good? Yes. I don't know. Okay. So, yes. Why? Uh-huh. 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 It has a 10% chance? It has a 1 in 3 chance of being hit. Yep. Yes, there's also there's a 2 in 3 chance that the inner ones get hit. Because there's 2 of them. Okay, okay. Why does probability matter? It doesn't really. If you can just accept the fact that they all have the same probability of being kicked out, and if you take a sample, if you take a sample, it's going to tell you how many electrons are at a particular distance from the nucleus. If it's not the same probability for all of them, then that's not going to be, you're not going to be able to use that peak to tell you what distance from the nucleus it is, because it would depend upon other factors, but it doesn't. Yeah? Cool. All right. So they're all moving with the same kinetic energy. So the photon has a kinetic energy. So we have the kinetic energy of the photon. Now, part of the energy is used to rip off one of the electrons. Yes? What do we call that energy? The energy to remove the electron. Ionization energy. And because we're going to use this term a lot in our next unit, we're going to start abbreviating it as IE, because nobody wants to write out ionization energy like 17 million times. Yes? Okay, so we have our ionization energy. And then we are going to have the kinetic energy of the electron that has been kicked out. Okay, so that's the kinetic energy of the photon that has been kicked, or electron that has been kicked out. So does it make sense then that if you were to say throw, I'm just going to make up some totally random numbers here, okay? They're not reality based at all, okay? Say I throw the kinetic energy of my photon and it is 12 kilojoules per mole, okay? Does it make sense then that if my ionization energy is 2 kilojoules per mole, then my kinetic energy of my photoelectron would be how much? 10 kilojoules per mole. Yes? Now, what if I had that same photon, 12 kilojoules per mole, but this time my ionization energy was 6 kilojoules per mole? Then this would be 6 kilojoules per mole. Okay? And if I was to draw, let's say we're looking again at our lithium atom. There's my nucleus. Let's call this electron 1, 2, and 3. Which equation would be the valid equation for electron 1? It's been absorbed. That's now potential energy of that electron. Than an electron that's sitting in the atom, yes. Yeah? Okay. Which equation for electron number 1? B, why? Yes. Yes. So I would like you to describe to your partner or someone near you why equation B is the correct choice for electron number 1 and not equation A. Okay, what do we think? Anyone want to try? Yes. Okay. So I like this statement, but what's my but? I'm always, always, always going to ask you why. Why? It does. Yeah, that's nice. Why? Okay, because it is closer to the nucleus. Bam! But you get the bam and swoop it. Yes, very nice. Okay. And I'm going to call it Coulombic attraction because AP like is in love with that term. Yes. You could call it electrostatic force or Coulombic attractive force. Yeah. I would say electrostatic over attractive because attractive could be gravitational. Do you know what I mean? Like I want to actually say it's related to the charges. And Coulombic attraction is, what are we actually going to say about Coulombic attraction here? That's nice, but what are we going to say to it in terms of how that relates to electron number one being closer to the nucleus and therefore having a higher ionization energy? I heard a word. Proportional. Oh, proportional to, yes, is proportional to the fish. Coulombic attraction is proportional to, actually it is, what word do I want to put in here? Which one, directly or inversely? What am I looking at here? I'm looking at closer to the nucleus. So I'm looking at the distance between the charges, yes? Yes, is inversely proportional to the distance between the charges. Yes, of course. I can also print this out for you at the end as well, okay? So Coulombic attraction is inversely proportional to the distance between the charges, and therefore the closer to the nucleus, the stronger the attractive force. I'm going to put a squared on there. If you weren't to put a squared on there, they would not, they're not concerned so much about that in the AP exam, but I'm going to put it there because we can. Yes, hang on, I'm going to finish the closer to the nucleus an electron is, the more tightly it is held. It is, like I said, in AP they probably don't care whether you mention the square or not. I'm going to mention the square. It is simply a law of nature that the force goes as the 1 over the square of the distance between the charges. So, yeah, I mean, when you looked at the data last day, right? When you doubled the distance, so when the distance was times 2, the force was 1 over 4, which is the same as 1 over 2 squared. When the distance was times 3, the force was 1 over 9, which is 1 over 3 squared. When the distance was 4, the force was 1 over 16, which was 1 over 4 squared. Yes? Yes. Yes. Yeah. It's inverse exponential. Yeah.
I know it's like
pH is fun. All right, so that's what we're looking at there. And AP is always going to be like, are you actually explaining from first principles, or are you saying it has a higher, it must be number 2 because it has a higher ionization energy? Do you know what I mean? Like, they always want you to dig that layer deeper and go back to first principles, go back to the forces. You're almost always going to be arguing in terms of forces when it comes to things like this. And that's going to go for the next unit, because in the next unit we will be looking at things like ionization energy for atoms, okay, and the periodic properties of that. All right, so these kind of arguments are going to come up again and again, and you want to use like that language around a Coulombic attraction, you know, being proportional to charge, being inversely proportional to the distance between the charges squared, or you'd not squared if you don't want to put that part in, okay? So here we have, that's our photoelectric effect. And so, what was I saying? Yeah, okay, so equation A, which electron would equation A correlate to? Number 3. So this would be electron 3, and this would be electron number 1 and 2. Okay, so now we're going to take a look at the graph, because you're always going to be given graphs for these things. So this is the intensity, okay, and I'm going to put, don't write this on any exam anywhere, okay, but this is basically the amount of electrons in a subshell. Just give me 1 second. Subshell. So it's intensity, because what's going to happen is once we have fired our light, at the atoms, and the electrons are coming out, those electrons are then going to go and bash into a detector, okay? The more bashes into a detector at a particular energy, the bigger the signal. That's the intensity, is the bigness of the signal. So the more bashing at a particular speed into the detector, the bigger the signal. Yes? That's not how they do it. They call it intensity, whatever. Just, the intensity is interpreted to mean the number of electrons, but it's not what's actually being measured. What's being measured is like, well, it is, I mean, it is how many, I don't know, just write intensity, okay?
But does that mean we always have whole numbers?
They'll always be whole numbers, yeah, because electrons don't come in halves. Okay, so remember down here, this area represents the nucleus. So over on the left, which is closest to the nucleus, and over here on the right, this is furthest from the nucleus. And what are we measuring on the bottom? Ionization energy. Ionization energy. It could also be called binding energy. Yes? Because it's the energy that binds that electron to the atom. And where are our big numbers going to be? Are our big numbers going to be close to the nucleus, or are our big numbers going to be far from the nucleus? They're going to be close, so that's why over here, this number is 0. Okay? 0 is like on the wrong side, right? Over here we have bigger numbers, and we have smaller numbers. Okay? So I'm going to just start drawing a bunch of photoelectron spectrums for like hydrogen, helium, lithium, beryllium, so that we can just sort of see them in a row, okay? So here is hydrogen. Here is helium. Oh, what happened? Did I draw it? Maybe like that. There we go. So what happened when we went from hydrogen to helium? We have 2 times as many electrons, so the height is twice as high. Let's just call this 1 here. Okay, and then we have 1, 2. Okay, so twice as high. Because there's two electrons. And up here we just had 1 electron. Now what else has happened to this peak? It's moved. Where has it moved? It has moved closer to the nucleus. It's moved to a higher energy, okay? And over here we have, of course, our lower energy. There's our hydrogen, there's our helium. Now what's going to happen with lithium with that same peak? Is it going to get higher? So here's hydrogen, Here's helium. There we have our hydrogen, we have our helium, we have our lithium. What, yes? It goes to the right? It goes to the left? What? Well, we only have one subshell so far. Well, hold on. So what's happening with lithium here? What is that first peak going to look like? Same height, why? Because this represents which subshell? 1s, and this is 1s1. This guy here now represents 1s2. Now, wouldn't it be nice if it was 1s3? But it's not. It's not 1s3. So this is going to say it's going to be the same height, but it's going to be a little bit to the left because it's moving closer to the nucleus. It's pulled closer to the nucleus by the 3 protons as opposed to 2 protons. Yes? It is, but that's not as large a factor. You mean the 2s subshell? What? We will talk about that, but we're not there yet. Okay? We're still only on hydrogen, right? Okay? Hydrogen, helium, lithium. So this is pulled closer to the nucleus. So we still have 1s2. So this one here is 1s2. And then we're going to have another peak. Is it going to be to the left or to the right? It's going to be to the right. And it's going to be how high? Half of that. Okay, so now we have 1s, or sorry, not 1s, 2s1. And in fact, I'm going to move it over a little bit because I want it to be like a little more obvious. So this is 2s1. Yes. Yes.
How do I know for a fact that none of that's there? When you go low, long enough, I will. But I would just
Sure. Yeah. Okay. So now we are moving on to who comes after lithium? Beryllium. So now we have 1s2 moving closer all the time. I'm not doing a very good job of that. I'm getting a little close here. 2s2. And actually, I do want to read up on that just a little bit because your question has made me wonder. Shush! I am thinking now, and when you all talk, I can't think. Okay? So just you may whisper to each other while I think. Okay? None of those. Okay. So I believe what's happening here, I honestly don't think they're going to ask you this, but when you have lithium, you have 1s like that, and then you have 2s. Okay? And this is where I get a little unhappy because I feel like I'm trying to make a judgment call on which thing is more important, and I'm not given particular direction by my resources as to why one factor is more important than the other. Okay? But when we have this one, this electron, this last electron that goes in is paired. Okay? And when it is paired, there is a little bit more electron-electron repulsion. And if there's more electron-electron repulsion, can you hold your question for a minute? If there's more electron-electron repulsion, what's that going to do to the ionization energy? It's going to lower it. But this is why it makes me unhappy, because I also have more protons. Yes? So I'm like, is the protons more important? Or is the electron-electron repulsion more important? I'm going to come back to you and get back to you on that, okay? Because I don't know why in some cases is more important and in other cases it's not. And I'm feeling like phooey. Do you know what I mean? Like, and I should be able to explain that in a coherent way to you. I'm going to talk with Ms. Wu and we'll see what we can come to. Yeah, so if you're, I believe, yeah, that does make a lot of sense. If you're further from the nucleus, probably the electron-electron repulsions matter more. And I will say that for sulfur, which is the one that you're looking at there, phosphorus and sulfur, so if we look at our electron diagram for phosphorus and sulfur, we have 1s, 2s. Oh, in fact, you know what? Let's just do it for nitrogen and oxygen instead, because it'll be the same thing. Okay? So if we have nitrogen and oxygen, so
I want you to take a look at this. This is where the important bit comes in. If you have carbon compared to nitrogen, so if we're comparing carbon and nitrogen, every electron is in its own orbital. Yes? Each electron gets its own orbital. In nitrogen, each electron in the 2p subshell also gets its own orbital. But when we get to oxygen, that next electron has to go into an already occupied orbital. And when that happens, when two electrons have to go into the same orbital, that results in extra electron-electron repulsion, as opposed to this one, which they're going into separate orbitals. So I believe that that's when you get that extra repulsion that then brings down your ionization energy. Not generally, okay? But the first pairing up of an electron in a subshell is, okay? It would go back up. So what you'll end up with then is, if we're looking at removing the outermost electrons, so we could remove this one, we could be removing this one, we would be removing one of these ones, okay? So we would have then the ionization energy trend for carbon would be, you know, we would have boron here, boron, carbon, it would be higher. Nitrogen, it would be higher yet. And then oxygen, it's going to go down, but not by like a whole lot, just a little bit, yeah. And then for chlorine, or what comes after oxygen, fluorine, we're going to be heading back in an upward trend again. Okay, so it's going to go like this. There's a little dip, and then it goes up again. Okay, these little dips are actually more part of our next unit. So I don't want you to worry about it for this test. Yes? Okay, yes. It just doesn't. This is not going to be on this test, so I don't really want to focus on it too much right now, because when we get to like talking about ionization energies, that's when this effect is going to become important. Yeah? And ionization energy is periodic trend, and our next unit is periodic trends. We're going to have a short interlude with Lewis structures, because I have not got your periodic trends workbook ready yet. And Lewis structures is a nice sort of thing that we can do just all on its own. Okay? All right. Morva, you look like, you're like, are you okay? Yeah? Okay, yes. No, not at all. Yeah. 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 I mean, when you see real graphs, they don't look anything like these graphs. They look like this. Like they don't look like normal, like you're looking at it, you're like, whoa, that looks nothing like in my textbook, right? Yeah, and there's like little bits and bobs happening here and there and squiggly bits, and yeah, a real one doesn't look anything like that. Shh. Yes, Janet. Yeah. Apparently it doesn't care. I don't know. Let's not worry about it because this is not part of this test. We will worry about that in the next test. Yes? Yes. It could be. We're not gonna fuss about it too much. Okay? Because at this point, you're not gonna have a question that looks like that. Yes? Okay. Yes. Okay. I'm going to give you practice problems. And then you'll be like, oh, these are the kind of questions we're going to get on this test. Oh, and in fact, I was going to give you some mass spec, and I made it this morning, and I was late running out the door, and yet it's not saved to my Dropbox, so I'm not giving it to you today, but I can post it today. Okay, so I'm going to go home and post it. All right? Okay. So at this point, how, other than the confusion that we've brought up, how are we feeling about PEZ? Do we understand what the peaks mean, where the zero is, all those things? If that is the case, then I would like you to please do the worksheet called Photoelectron Spectroscopy and Electron Configuration on 9.4b, please. 9.4b. I love the AP curriculum. They give us this stuff